artificial variable and surplus variable. So these two are the main conditions for the big M method. And for the two-phase method, we will be using the same two conditions because it is an extension of the big M. One part of it belongs to the big M and the other part of it belongs to the simplex. So that is how these two relate. So the first condition is that it can be either maximum or minimum one. So it doesn't matter, unlike simplex. And the other thing is that the constraints will be like greater than or equal to and equal to. If these two constraints are given, we will use the big M method or we will use the two-phase method. But the instructor in the paper, he may be directing you to use which method. He may announce it to do the two-phase method or do the big M method or do simple simplex method. So if we have like a minimization function, but it's a simplex, then you will have to convert it into the maximization problem. But if the teacher has given you the question like do it on big M or two-phase method, but it is a minimization, so you don't have to actually bother about converting it to maximization and then doing it. So we can do it right over there using the minimization also. So these two are the conditions that must be met in order to use the two-phase method. Now, uh, in the book, it is page number 115, and this is the example that we will be using. Actually, it is not solved over here, but I will. It has just given the final solutions of it. But I will go step by step, and I will be explain it step by step to so that we can learn it. Okay, so the first, the two-phase method, as the name of the method suggests, it has two basic steps or two phases of it. The first phase or phase one, actually, it belongs to the big M method, and in big M method, what we actually do is that we add surplus and slack variables along with artificial variables. Can you tell me where we will add the artificial variable? Yes, in the constraint, but it in which constraint? What type of constraint? No, it is in the greater than or equal to or in simple equal to. Anywhere where we cannot add the slack variable, we need to put the surplus variable, and along with surplus variable, we must add the artificial variable. I will do it over here. Okay. So we have the problem as minimize z, and the function is 4x1 plus x2 subject to 3x1 plus x2 is equal to 3 4x1 plus 3x2 greater than or equal to 6 and x1 plus 2x2 less than or equal to 4, while x1, x2 are greater than or equal to 0. It is mandatory non-negative constant. So can you, for example, I name it 1, constant 1, I name it constant 2, and I name it constant 3. So can you tell me in which constraint we will add the slack variable? Yes, the 3. In the third one, we will add the slack variable. And at which one will subtract the surplus variable? Yes, in the 2 we will subtract the surplus variable. And at which one we will just add the artificial variable? 1. Yes. Good, thank you. Now we will proceed to the making the standard form of it. Making standardized form. Actually, it's my kind of, teaching process, to engage, students or, friends in the conversation in the. Okay. So actually, from this, I understand that, you have understood this part of the process and, you like over here. So I focus then on emphasize on that part where you don't answer me either, or, you tell me that, okay, I haven't, looked at it. I haven't studied it. So I emphasize on that part of it. Yeah. So when I used to teach in college, I also, did the same with the students. So this is kind of, built in me. So that is okay. So now we will make the standardized form of it. And by the standardized, I mean that, using the same objective functions and constants, but we will add the slack variables and we will add artificial variable while subtracting the surplus variable. And as you mentioned, we can make it as follows. For example, yes, minimize z is equal to, we will leave it blank. We will first process the constraints, and then from the constraints, we will put it into the objective function. Okay, so the first constraint is 3x1 plus x2 is equal to 3. Now we have equal to sign, so we cannot add the slack variable, we cannot subtract the surplus variable, but we will add an artificial variable here. So we will write it as follows: a3 plus a1 is equal to 3. Now this is the first constraint, complete constraint in standardized form. The second one is 4x1 plus 3x2. Now this is greater than or equal to 6. So here we will subtract surplus variable and add artificial variable. Now subtracting S1 but adding A2. Now this is the second complete constraint in standardized form. Now the third one is x1 plus 2x2 less than or equal to 4. So we just have to add the slack variable, equate it to the right hand side. Sorry, I didn't write the right hand side over here, so I will write it. And this is the third complete standardized constraint. Now we have all the surplus and slack and artificial variables. So now we can add it to the minimization function. So the minimization function will be as follows. plus. Now we first put A1, so I will write 0 A1 over here plus then S1 0 A2 plus 0 S2. So this is now in the standardized form. Now we will make a table of it, and then we will, you know, we will do the first phase of the two-phase method. So let me make the standardized table of it. Now we will make the standardized. We also call it the simplex table. So we will make the standardized table, and here we will have the basic variables. And in the basic variable, we have here uh, normally we have z over here, but here we will write r because we will change the objective function over here. We will change it in the two-phase method. Actually, we in the first phase we change the objective function of it. We solve it for R1 and R2, and then we substitute the value of R1 and R2 into the constraints and solve the second phase of it. So here it will become this function, minimize b, this, it will become R. From R, Ra, I mean the artificial variable. So, and it will be equal to, we have actually two artificial variables over here. So it will be equal to A1 plus A2. And in standardized form, it will be equal to, and will be equal to 0, R minus A1, A2, and it is equal to 0. So now we can put the coefficients of this equation, this objective function, this artificial objective function, and we will put it over here. So here we will have x1, x2, just like the simplex method. We have two variables, then we have artificial variables of a1, a2, and we have s1 as the surplus variable and s2 as the slack variable. And then we have the right hand side and a ratio. Now, in the objective function, the new objective function that we made, just adding the artificial variables that we put over here, the coefficient for x1 in this function is 0. The coefficient of x2 is also 0. The coefficient of a1 is -1. The coefficient of a2 is also -1, and s1 is 0, s2 is 0, and the right hand side is also 0. Now, the first constraints where we put a1, now we will put the coefficients of it into this one. So it will be a1, a2, and s2. We ignored the s1 over here because s1 is surplus. So this is a minimization function, okay? And we will ignore the surplus variables. We just only entertain the slack variables, okay? So now the coefficient of x1 in the first variable, constraint is 3. The coefficient of x2 in first constraint is 1, a1 is also 1, a2 is 0, s1 is 0, and s2 is also 0, and the right hand side is equal to 3. So we will put 3 over here. For a2, the second constraint, we have x1 coefficient equal to 4. So we will write 4 over here. Then we will write 3 S1 is minus 1 and A2 is 1. All others are 0 and the right hand side is equal to 6. Now for the S2, where we put the S2, it is the third constraint. So in third constraint, the X1 is 1, the X2 is 2, S2 is 1 and the rest are 0 and the right hand side is equal to 4. So this is now the standard table for the artificial objective function that we made in the first phase of it. This is the starting of the first phase, but we cannot solve it using this table. Why we cannot solve it? Can you answer me? Yeah, we cannot solve it in this condition. Why we cannot solve it? Just look into the R row and answer me if you know the reason behind it. Yes, because zeros and negatives. In minimization function, we what we look for is the maximum positive value in the R 0. In the Z row or in the R artificial row, we look for the most positive ones. And here we see that all others are 0 and the artificial variables are minus 1 and minus 1. So there is nothing to pick. So we cannot define the entering variable and the leaving variables over here. So what we will do is we will get rid of these artificial variables in the R row. In this row, we will make this minus 1 and minus 1 equal to 0 using the row operations, right? Yeah. So remember this point. We have to get rid of the artificial variables when we define the first phase of it. When we define the first phase and the first table, we need to get rid of A1 and A2 in the R row. This is the very important point that you must learn in order to be able to, solve questions in exams and also in, for just a general understanding. You must get rid of the artificial variables. Now, how we will get rid of these artificial variables? We see that artificial variables here is minus 1 and just beneath minus 1 we have 1 over here. So what if we add R row to A1 row? So this minus 1 will be added to 1 and we will get over here is 0. You understand? And the second artificial variable is also minus 1 and beneath this is 0, but beneath that other one is 1. So we have a 1 in the A2 row. So we can add both of these A1 row and A2 row to the R row and we will get rid of A1 and A2 altogether and it will become 0, 0. So we will use this row function to get rid of the A1 and A2. So what we do is we define new R row which is equal to old R row plus A1 row plus A2 row. Now A1 row is 3110003, but the old R row is 0, 0, minus 1, minus 1, 0, 0, and 0. The A1 row over here is 3, 1, 1, 0, 0, 0 and 3, we will also add the A2 row, which is equal to 4, 3, 0, 1, minus 1, 0, and 6. So first we will add A1 and A2 row together, and then the addition of both of these we will add to the old R row to get the new R row. So what we will do here is 0, 0, minus 1, minus 1, 0, 0, 0. This is the old R row plus. Now we will add A1 and A2 row, and then we will add the sum of it to the old R row. So it will be summed as follows. 3 plus 4 is 7, 1 plus 3 is 4, 1 plus 0 is 0, 0 plus 1 is 1, 0 plus minus 1 is minus 1, 0 plus 0 is 0, and 3 plus 6 is 9. Now we will do this operation. 0 plus 7 is 7, 0 plus 4 is 4, minus 1 plus 0 is minus 1. Sorry, we got something wrong over here. 311,431. So 1 plus 0 is 1. So it is 7411 minus 109. So minus 1 plus 1 is 0. Minus 1 plus 1 is 0. So we get rid of A1 and A2 over here. Now going to the next one, we get 0 plus minus 1 is minus 1. 0 plus 0 is 0, and 0 plus 9 is 9. So this is the new R row. We will update the new R row in the next table. We will make a table and we will update it. So we will get the basic variable. We will get x1, x2, a1, a2, s1, and s2. This is the right hand side, and this is the ratio. Now here we have R instead of Z, and we have here a1, a2, and s2. Now the updated R row is 7, 4, 0, 0, minus 1, 0, and the right hand side is equal to 9. And we will write the other constants as it is. We don't need to change any of the other thing, which is 3, 1, 1, just copying the first table that we made. Okay. The other one is 4, 3, 0, 1, minus 1, 0, and 6. And the S2 row is 1, 2, triple 0, 1, and 4. Now we see that we have got some positives over here, and this is minimization problem. So now we can define the entering variable and the leaving variables over here. So it is minimization function. Which of the variable will be the entering variable? Can you please tell me? Yeah, which one will be the entering variable? And this is minimization function. Yes, x1. This x1 will be entering variable. This is entering variable, and this column actually is the pivot column. Now this is the pivot column. Now we will use the ratio method to define the leaving variable of it. For now, in the ratios, we will ignore the R row, and we will make the ratios for the only the artificial variables and the slack variable. So the ratio over here is 3. Now, you were confused yesterday that which coefficient I will use. So this is the pivot column. So 7 is the coefficient for the R row. If we are doing the ratio operation for the A1 row, so 3 is the coefficient over here, 4 is the coefficient for A2, and 1 is the coefficient for S2. So 3 by 3 is equal to 1, 6 by 4 is equal to something 1.2 or something, and 4 by 1 is equal to 4. So this one is the minimum one. It will be equal to something 1.5, I guess. 6 by 4. Let me. Yes, 1.5. So this one is the minimum positive. So A1 will be the leaving variable. And this one is actually the pivot row. Now the intersection of the pivot column and pivot row is pivot element or pivot key element. So now the pivot key element is equal to 3. So we will define first the new pivot row, which is equal to the old pivot row divided by 3. Now the old pivot is 3, 1, 1, 0, 0, 0, and 3 divided by 3. What we get here is 1, 1 over 3, 1 over 3, 0, 0, 0, and 1. So we will make a new table for this first iteration, and we will update the pivot row. So here now instead of A1 we will write X1 over here because X1 will enter the system. We'll write A2 and S2. We will write X1, X2, A1, A2, S1, S2. We will write the right hand side and then we will write the ratio. Okay. So now the new pivot row is 1, 1 over 3, 1 over 3, 0, 0, 0, and the right hand side is equal to 1. So now we need to do is to make all the row operations for the R, A2, and S2 rows. So first of all, we will make the new R row. New R row is equal to old R row minus pivot column coefficient into new pivot row. Now the old is 7, 4, 0, 0, minus 1, 0, and 9 minus the pivot element is 7 into the new pivot row is 1, 1 over 3, 1 over 3, 0, 0, 0, and 1. So the new R, yes, the new pivot row, this one, we will have to take it with all the other 3 rows for the updating. Yes, yes, this one factor will not change. By updating all the other threes, you have to use the same new pivot row. And then in the next iteration, whatever the new pivot row is, you have to use that one. Yes. So we have here is the new R row, and it is equal to 7 minus 7 is 0. 4 minus 7 by 3, it will give us 4 minus 7 by 3, it will give us 5 by 3. And 0 minus 7 by 3 is minus 7 by 3. And minus 1 plus minus 1 minus 7 by 7 into 0, so it will become minus 1. And 0 minus 0 is 0. 0 and 9 minus 7 is 2. So this is the new updated R row. We will update this one into this table over here. We will get 0, 5 by 3, minus 7 by 3, minus 1. Is, A1 is 0, minus 1, 0, and the right hand side will become 2. Okay, what we noticed over here is that the final solution, first it was 9, and now okay, so here the right hand side of 9, it will change to 2. This is the feasible solution that we get, but it is not optimal solution. We will get the optimal solution when we get 0 over here, because we want to minimize. So when we get 0 over here, the iterations will stop and we need to then go to the second phase of it. Okay. Now we will update the A2 row. So the new A2 or A2 star is equal to old A2 minus pivot column coefficient into new pivot row. Now the old A2 is 4, 3, 0, 1, minus 1, 0, and 6, minus the pivot coefficient over here is 4. So the new pivot row is 1 by 3, 1 by 3, 0, 0, 0, and 1. We will use the same new pivot row against all to update in that iteration. For the next iteration, it will change because we will get the new pivot row. So using the row operations, we get here is 4 minus 4 is 0, 3 minus 4 by 3 is get LCM 3, 9 minus 4 is equal to 5. So it is equal to 5 by 3. 0 minus 4 by 3 is minus 4 by 3. 1 minus 0 is 0, minus 1 minus 0 -1. Okay, 4 minus 4 is 0. 3 minus 4 into 3 is equal to 5 by 3. 0 minus 4 by 3 is minus 4 by 3. 1 minus 0 is 0. Minus 1 minus 0 is minus 1. 0 minus 0 is 0. And 6 minus 4 is 2. So this is the updated one. Now we will update this one into the table. We will incorporate it over here. So the values are 0. For x2, we got the value of 5 by 3 minus 4 by 3 minus 1. 0 and 2. Minus 1, 0. Four, 3, 0, 1, 0 is 1 minus, we got 4 by 3. This is 1, 0, minus 1. This 1 minus 4 into 0 is minus 1, 0. Okay. We will update the values. 1, this is minus 1, this is 0. Pardon me because I have to, check every value, because at the end we have to, check the results of it. So I'm verifying it. So now I got it right. Yes, I got it right now. So now we will update the S2 row also. For S2 new is equal to S2 old minus the pivot column coefficient into new pivot row. So the S2 old is 120014. 1200 and 1 4. Yes. And then the pivot column coefficient is 1, and the new pivot row is 1, 1 over 3, 1 over 3, 0, 0, 0, and 1. So doing this, we get the ST new as 0, 1 minus 1 is 0, 2 minus 1 over 3 is 5 by 3, and 0 minus 1 over 3 is minus 1 over 3, 0 minus 0 is 0, 0 minus 0 is also 0, 1 minus 0 is 1, and 4 minus 1 is 3. So we need to update this value, the S2 static or new, into the previous table. So here we are. This is the value that we get, which is 0, 5 by 3 minus 1 over 3, 0, 0, 1, and 3. Now, in this table, this is the updated table. Now we will do the second iteration of it, and we'll find out which one is the entering variable and which one is the leaving variable. So it is the minimization problem. So we will select the most positive, the positive and the largest one. So this is x2, the corresponding value to x2, the coefficient of x2 in our row is the highest one and is positive. So the entering variable is x2 in this iteration. So the entering variable is x2. Now we will find the leaving variable using the ratio method. Now the ratio is over here. Okay, so in the ratios we ignore actually the z or r row. So we will term this column as the pivot column. So now 1, we will divide this one with the 1 divided by 1 by 3 is 3, and 2 divided by 5 by 3 is 6 by 5. Uh, yeah, 6 by 5, which gives us something 1.2 or something. And this one is 3 by 5 by 3, which gives us 9 by 5, which gives us 1.8 or something. So this is the minimum one, minimum positive. So the minimum positive is A2. So A2 here is the leaving variable. So we will update it over here and we will term it as that A2, the artificial variable second one, is the leaving variable. So now the updated table, the basic variable, and here we will write the R, X1, X2, A1, A2, S1, and S2, the right hand side, and ratio. Now, what we will do is we will be adding the x2 in this column, and the other one is s2 because it entered the system and a2 left the system. So now we will have the updated or new pivot row. We know that a2 here is the leaving variable, so this one is actually the pivot row. So the intersection of pivot column and pivot row is 5 by 3. So the pivot element is, it is equal to old pivot row divided by pivot element or key element. So now the pivot element is 5 by 3 and the old pivot row is 0, 5 by 3, minus 4 by 3, minus 1, minus 1, 0, and 2. So doing this division, we get 0, 1, minus 4 by 3 and minus 5 by 3 divided by 5 by 3, we get minus 4 by 5. 3 and 3 will be cancelled. So minus 1 divided by 5 by 3 is equal to actually minus 3 by 5. Similarly, we also get minus 3 by 5 over here. And 0 divided by 5 by 3, we get 0. And 2 divided by 5 by 3 is equal to 6 by 5. So this is the new or updated pivot row for the second iteration. So now we will update the row in this table. So for x1 we get 0 coefficient, for x2 we get 1, for a1 we get minus 4 by 5, and for a2 we get minus 3 by 5. For s2 we also get minus 3 by 5. For s2 we got 0. In the right hand side we get 6 by 5. Now according to this new pivot row, we will update all of the above and below rows. So the first row that we will update is the R row. Now the R row is equal to old R row minus the pivot column coefficient into new or updated pivot row. So it will give us something like this. Let me write it down. 0, the old row is equal to 0, 5 by 3 minus 7 by 3, 0 minus 1, 0 and 2. The pivot element is 5 by 3 and the new pivot row is this one. So we will write it over here. Now we will do this row operations and we will find out the new R row. So the new R row is equal to 0 minus 5 by 3 into 0 is equal to 0. So 0 minus 0 is 0. The second one will be 5 by 3 minus 5 by 3, which will also give us 0. The third one will be minus 7 by 3 minus 5 by 3 into minus 4 by 5. It will give you 20 by 15. So minus 7 by 3 plus minus and minus will give us plus. The other one will be 0 plus 1. The minus 1 plus 1, 0. And the last one is 2 minus 5 by 3 into 6 by 5. Now doing this row operation, we will get the final result as 0. 5 by 3 minus 5 by 3 will also give us 0. Minus 7 by 3 plus 20 by 15, it will give a LCM of 15. So, and minus 7 by 3 into 15, it will give 7 5 or 35 minus 35 plus 20. So it will give us minus 15 divided by 15. So it will give us minus 1. Now 0 plus 1 is 1, minus 1 plus 1 is 0, 0, and 2 minus 5 by 3 into 5 into 6 is 30, and 3 into 5 is 15. So it will give us 2. So 2 minus 2 is also 0. So this is the new R row. Now we will update this value into the table. So the table value here we get is 0, 0, minus 1, 1, 0, 0, and 0. Now this is the point where we realize that when the right hand side of the R row is 0 in minimization, it means that the final solution of the phase 1 has arrived. So this is the indication of it. Now we will update the x1 and s2 rows using the same operation, and then we will switch to the next phase of it, the second phase of it. So now first update the x1 row. So the new x1 row or x1 static is equal to old x1 minus the pivot column coefficient into new pivot row. From the table, we get that the old x1 is 1, 1 over 3, 1 over 3, 0, 0, 0, 1, minus the pivot column is 1 over 3. Now the new pivot row is 0, 1, minus 4 by 5, minus 3 by 5, minus 3 by 5, 0 and 6 by 5. So now doing this row operation, we get 1 minus 1 by 3 into 0 is 1 minus 0, which gives us 1. 1 divided by 3 minus 1 by 3. So it will give us 0. 1 over 3 minus 1 over 3 into minus 4 by 5. So minus and minus will give us plus, and 1 into 4 is 4 and 3 into 5 is 15. So it will give us 1 divided by 3 plus 4 by 15. So 1 divided by 3 plus 4 by 15, it will give us, the LCM will be 15. So it will give us 9 by 15. Now 0 minus 1 over 3 into minus 3 by 5. It will give us 0 plus 3 by 15, which is given 1 over 5. So similarly, the next one will also give us 1 over 5 because it is same. And 0 minus 1 over 3 into 0 is 0. And 1 minus 1 over 3 into 6 by 5, it will give us 1 over 3 into 6 by 5. So it will give us 1 minus 6 by 15. So the LCM will be 15, and it will give us 15 minus 6 is equal to 9. So it will give us 9 by 15. So then x1 steric is equal to the updated is 1, 0, 9 by 15, 1 over 5, 1 over 5, 0, and 9 by 15. So we will update this value into the table. Into the table we put 1, 0, 9 by 15, 1 by 5, 1 by 5, 0, and 9 by 15. So now we will update the S2 one. We will update the S2 row. So the new S2 or updated S2, I will denote it as double asterisk is equal to old S2 minus the pivot column coefficient into the new pivot row. So the old S2 from the table is 0, 5 by 3, 1 by 3, 0, 0, 1, and 3 minus the pivot coefficient is 5 by 3 into the new pivot row. New pivot row we can write from the above. From this one is 0, 1 minus 4 by 5 minus 3 by 5 minus 3 by 5, 0, and 6 by 5. So now doing this operation, what we get is 0, 0, 1 over 3 minus 5 by 3 into minus 4 by 5. So minus and minus will give us plus. 5 into 4 is 20 and 3 into 5 is 15. So 1 over 3 plus 20 by 15. So it will give us 15. It will give us something like 20. This is minus 1 over 3. So it will give us uh, minus 5 Yes, yes. Okay, just let me write this, you know, and then we can move on. Okay, I will move on to the next step of the this two-phase problem. But let me just conclude it. Yes. Getting this one, get 0, 15, 1. We see that we got the right hand side at 0. So this is the point where the solution has arrived for the phase 1. Okay, now we have solved it for the R1, R2. Now we will solve it for the actual model, the actual problem. Okay, so going to the phase 2 of the problem. Here we switch to the phase 2 because we have got a feasible solution in the phase 1. Now in this table, if we see this table, the first constraint over here is the coefficient for x1 is 1. So I will make a constraint out of it. So the coefficient of x1 is 1, x2 is 0, a1 is 1 by 15, a2 is 1 over 5, s1 is 1 over 5. So we will ignore the a1 and a2 because we don't need it. Okay, after the step, you just these two needs to be ignored. Okay, so now we will make an equation out of it. So x1 is 1, so we will put it like that. x1 plus, we need only the slack variable. We don't need surplus and we don't need the artificial variables. And for the slack, we know that slack is 1 over 5, and it is giving us 9 by 15 on the right hand side. I wrote it from here. 1 over 5 is equal to 9 by 15. Similarly, just for a second constraint, we have an equation as like x2, ignore these two, so x2 minus 3 by 5, s1 is equal to 6 by 5. So we will have like x2 minus 3 by 5, s1 is equal to 6 by 5. And for the third one, we have it like here s1 is 1, s2 is 1, and the right hand side is also 1. So we will get s1 plus s2 is equal to 1. So these are the three new constraints in the phase 2. Okay, so now we will write the original equation, which was minimize z is equal to 4x1 plus x2, and make the table for these constraints and this objective function. Now here we will do the just like we did in the simplex method. Now we will write over here is z x1 x2 and s2 here x1 x2, and we have two variable s1 sn2, and we will ignore the a1 and a2. Okay, so now here we write the right hand side and then the ratio here. um, okay, so yes, so do you understand how I wrote these three constraints from the final table? That was something I want to to show you. Using this table, actually this is the final table that we got. Yes, so in this, yes, so the a1 and a2, these two needs to be ignored. So don't write, actually you can make another table without writing this a1 and a2 column in it. That will be a kind of easy for you. And then because these are artificial variables, we have solved it for these a1 and a2. Now we want to solve it for x1 and x2. So out of these, we want to find out the x1 and x2 and s2 slack variables and the basic variables. We ignore a1 and a2. Artificial variables are ignored in the second step. Yes. So here we see that the coefficient for x1 in the x1 row is 1, while the x2 is 0. So x2 is also ignored over here. 1 over 5 for s1 and 0 for s2. So s2 and x2 needs to be ignored. We just need to write x1 plus 1 over 5 into s1 is equal to 9 by 15. This must be the first constraint for this system now. Just like we write over here, x1 plus 1 over 5 into s1 is 9 by 15. And we wrote it from here, x1 plus 1 over 5 s1 is equal to 9 by 15. Similarly, doing it for the second one, x2 variable, x2 minus 3 by 5 into s1 is 6 by 5. And this is the constraint. x2 minus 3 by 5 into s1 is 6 by 5. The third one is the x1 is 0, x2 is 0, a1 and a2 are ignored, and we have s1 is equal to 1, s2 is equal to 1, and right hand side is equal to 1. So s1 plus s2 is equal to 1. That is how I came up with all these constraints. We understand now? Yes, the final solution of the phase 1 will give you these next constraints that we will use in the next W. So now writing the objective function into the standard form we will get is z minus 4x1 minus x2 plus 0s1 and plus 0s2. Okay, so here the variable, the coefficient for x1 will be in the objective function is -4. This is -1. S1 is 0. S2 is also 0, and the right hand side is also 0. For x1 is here, it is 1. X2 is 0. S1 is 1 over 5. S2 is 0, and the right hand side is 9 by 15, or you can write it as 3 by 5, which are equal. For x2, the second constraint, we have x1 is equal to 0, so we will write x1 is equal to 0. For x2, we have 1. For s1, we have minus 3 by 5. For s2, we have 0, and the right hand side is 6 by 5. Now, for s2, the last one constraint, s1 is 1, s2 is 1, x1 is 0, and x2 is also 0. So we will write over here is 0, 0, 1, 1, and the right hand side is also 1. Now, we just need to do is only one iteration. Okay, we just need to have the x1 and x2 need to be equal to 0, just like we did it for the a1 and a2. We just need to do one row operation that makes x1 and x2 equal to 0. So how can we make it 0? We can make it 0 by multiplying x1 with 4 and then adding it to the 0. Similarly, here it is -1 and here it is 1. So just adding 0 with the x2 row, it can make this -1 into 0. And if we multiply x1 with 4 and add it with z, it will make -4 into 0. So using this row operation, new z row in which x1 and x2 are 0 is equal to old z row minus 4 into x1 row plus x2 row. Now doing this operation, we get -4, -1, 0, 0, and 0 minus 4 into x1 is 1, 0, 1 over 5, 0, and 9 by 15. And the third one is plus x2 row. X2 row is 0, 1, minus 3 by 5, 0, and 6 by 5. So doing the first operation, we get is -4 to add it because it is minus. So -4 plus 4, it will become 0. -1 plus 4 into 0 is -1. 0 plus 4 by 5 is 4 by 5. And 0 plus 0, 0 is 0. And 0 plus 4 into 9 by 5 is, will give us 12 by 5. Now plus 0, 1, minus 3 by 5, 0, and 6 by 5. Now in this operation we get 0, -1, 4 by 5, 0, 12 by 5, plus 0, 1, minus 3 by 5, 0, and 6 by 5. It will give us 0, 0, 4 by 5, and minus 3 by 5. It will give us 1 by 5. 0 plus 0 will give 0, and 12 by 5 plus 6 by 5, it will give Z row. So this is the new Z row, but we just need to make one more iteration. So should I do it or should I skip it? It will be okay. Just it is just one iteration, but it is important. So now in the Z, the new Z is 0, 0, 1 by 5, 0 and 18 5. 0, 1 over 5, 0 and 18 by 5. The X1 is we don't need to change the other one. You just need to get rid of the negatives x1 and x2 and the 0. Here we get 0, 1, minus 3 by 5, 0 and 6 by 5, and 0, 0, 1, 1 and 1. Now we see that there is no higher positives. So this is actually the optimal solution. The optimal solution is 18 by 5, which is equal to Z, and x1 is 3 by 5, x2 is 6 by 5. This is the final solution of it. So that is how we do the two-phase method. This is just the only iteration that we need to do in the two-phase method in the second phase. But the important thing is the translation of these constraints from the final table. We got the final table over here. We just need to translate the constraints from here into the new one and then make the table and make the x1 and x2 equal to 0 using some row operation, and that row operation will be the final result. So that is all for the two-phase method. So did you get some of the points of the two-phase method, or it is yes, some difference in the first first phase, the very first kind of first iteration is different, and in the second one, before starting the first iteration, the makeup is different. The first thing that we do, making the constraints out of the final table, that is kind of a tricky thing in the two-phase method. Else is all the simplex method. It's same thing. So please work on it, and if you have any problem, you can just put your question and I can answer it. I can help you with that particular thing. So besides this two-phase method, I also wanted to do the degenerate solutions, the special cases. I will do one special case today, and inshallah, day after tomorrow, I will do the three other special cases, and then we will go to the sensitivity analysis, and inshallah, the sensitivity analysis will be covered in like 2 hours or 3 hours lecture. Okay. You hear me? 12 p.m. Um, can it be like 2 or 2:30? Your time 3:30. Okay. We can arrange it. Okay. I will look into my, so inshallah, hopefully we will arrange it. If not, we can do it like day after tomorrow or in the night if it's possible for you. So I will do the first special case of the simplex model, that is the degenerate solution. So the degenerate solution, just like the name suggests, degenerate. It means that the answer of the simplex model, it will be stuck at some point, like one of the basic variable will become zero and the answer will remain same. Like you will make like 20 or more than 20 iterations, but the answer will be the same. It will not move. So these kind of solutions are the degenerate solutions or degeneracy. The phenomena is called degeneracy. The degenerate solution. So it happens when we have like two things. First is when we, that in the simplex method, when we define the entering variable, we do the ratios. So when the ratios for the two variables are same, it means that it will develop at some point, it will develop the degenerate solution. So you will make the iteration, but the final solution, it will not change. And the second condition is that one of the basic variable will have the value of zero. So these two are the conditions, are the principles of the degenerate solution. So the first thing is when a tie occur between two basic variables. Okay. Yes. Okay. And the second is when the solution is solution for one of the basic variable is equal to zero. So these two are the conditions for the degenerate solutions or the degeneracy to occur. The first thing is when a tie occur between two basic variables, and the second thing is when the solution for one of the basic variables, either x1 or x2 or some slack, it becomes zero. Then the degenerate solution starts to occur. It will not change. The right hand side of the Z row will not change, like no matter how many iterations do you make after that, it will not change. So this kind of phenomena is called degeneracy. Okay, so I will make an iteration or two of an example, and I will show you how the degeneracy occurs in the simplex models. A tie means like when two values are same. I will show you like how the tie occurs. Uh, the page is 118, and the example is 3.5-1. Okay, now it says maximize z is equal to 3x1 plus 9x2 subject to x1 plus 4x2 less than or equal to 8, x1 plus 2x2 less than or equal to 4, and x1, x2 greater than or equal to 0. So it is a classical simplex model because all the constraints are in less than or equal to sign, and it is a maximization problem. So all the constraints and the objective function meet the criteria of a simplex model. So now we will make an iteration and I will show you how the tie occurs. Okay. So the iteration will be like we will have like basic variables, and here we have z, x1, x2, we have two variables, and here we will add s1 and here we will add s2. I'm not actually writing it, just to save time. You know the procedure of it, how to, add the slack variable. Or should I write it completely? Here we will, 0s1 plus 0s2. Okay. And in the standard form, it will be like z minus 3x1 minus 9x2 plus 0s1 plus 0s2. You know the standard form of it. So here the variable will be minus 3 minus 9 s1 s2. Here will be the right hand side, and the ratio. Here the basic variables are s1 and s2 because these are the slack variables. So now s1 is 0, s2 is 0, and the right hand side is also 0. x1 here is 1, 4, it is 1, it is 0, it is 0, it is 1 over here, and here it is 1 and 2, and the right hand side is 8 and 4. So now, as it is a maximization problem, so we will have to find the maximum negative one. So the maximum negative one among all these is minus 9, the maximum negative. So x2 is the entering variable. Now, for the leaving variable, we need to find the ratios of it. For the ratios, we have 8 by 4. This is the pivot column. Okay, 8 by 4, which is equal to 2, and 4 by 2, which is also is equal to 2. So this is called tie. Now you see what is tie. So now this ratio is equal to this ratio. So the ratio for S1 and S2 basic variables is actually same. So we know that this simplex will, it will form the degenerate solution in the next iteration. So for the next iteration, you can select any of it as the leaving variable, whatever you want to. Okay, for example, S1 we selected as the leaving variable. So this is the key element. The key element is key pivot element, which is at the intersection of the pivot column and pivot row is equal to 4. So the new pivot row is equal to old divided by 4. The old one is 1, 4, 1, 0, and 8. Divided by 4, it will give us 1 over 4, 1, 1 over 4, 0, and 2. So we need to make another table, and we should write it as Z S1. We will update it to X2, and we'll write S2 over here, X1, X2, S1, and S2 will have the right hand side over here, and we will have the ratio over here. Now the X2 over here updated is 1 over 4, 1, 1 over 4, 0, and 2. Now the new Z row is equal to, we need to find the new Z row, which is equal to the old Z minus pivot column coefficient into the new pivot row. So we will write it over here as minus 3, minus 9, 0, 0, 0, minus the pivot element is minus 9 into the new pivot row is 1 over 4, 1, 1 over 4, 0, and 2. So doing this row operation, we will find the Z row and update it over here. The Z row will be minus 3 plus 9 by 4. It will give us minus 3 plus 9 by 4. It will give us like minus 12 plus 9 divided by 4, which is equal to minus 3 by 4. So here we will get minus 3 by 4. It will become 0, and the other one will become 9 by 4. The other one will become 0, and the right hand side will be 0 plus 9 into 2, 18. So it will give us 18 over here. Okay. So now the S2 row, updated S2 row, S2 new is equal to S2 old minus pivot column coefficient into new pivot row. So the S2 old is 12014, 1201 and 4 minus the pivot column is pivot coefficient is 2, and the new pivot row is 1 over 4, 1, 1 over 4, 0, 2. 1 over 4, 1, 1 over 4, 0, and 2. So doing this row operation, we will get the new S2 row, which is S2 star. So it is 1 minus 2 by 4 is 1 by 2. 1 minus 1 by 2 is 1 by 2. And 2 minus 2 by 4, 2 minus 2 is equal to 0. 0 minus 2 into 1 by 4 minus 1 over 2. 1 minus 2 into 0 is equal to 1. And 4 minus 4 is also equal to 0. So the updated table is 1 over 2, 0 minus 1 over 2, 1, 0. 1 over 2, 0 minus 1 over 2, 1 and 0. Now, what condition did we have in the degenerate solution? That when a tie occur between two, so here we got a tie. And the second one was when the solution for one of the basic variable is 0. So now the solution for S2, that is basic variable, is 0. You see that? So the both of the conditions are met actually. It is not important that it should meet both the condition, but at some point it will meet both the conditions. So we had a tie, and then we have a basic variable S2 that has a solution right hand side equal to 0. Now we will do one more iteration, and we will see that the right hand side for the Z row will remain 18 and it will not change. Okay. So now, so now, as it is a maximization function, so the most negative one is x1 over here. So x1 is the entering variable, and the leaving variable will be defined by the ratio. Now the ratio will be 2 divided by 1 over 4. It will be equal to 8, and 0 divided by 1 over 2 will be equal to 0. So now the minimum positive is this one. Minimum positive. So S2 is the leaving variable over here. Now we will update it and we will see that the right hand side of the 0 remains the same whatever we do. It will not change. And it will show that this solution is a degenerate solution. Now going to the second iteration of it, we will update the table over here. Basic variable. We will have Z. We already had X2, and here we will have X1, and here we will have X1, X2, S1 and S2, and we will have the right hand side and ratio. Now the new pivot row, that is the X1 row, we need to find. So the new pivot row is equal to old divided by the pivot element. So the old one is 1 over 2, 0 minus 1 over 2, 1 and 0. 1 over 2, 0 minus 1 over 2, 1 and 0, and it will be divided by 1 over 2. So what we will get over here is 1, 0 minus 1, 2 and 0. This is what we get for this row, and we will update it over here. So it is 1, 0 minus 1, 2 and 0. You see, the right hand side is again 0. Yes, so it will not change the right hand side solution, and it will, repeat it. Whatever you do, you cannot, increase or decrease the, what we say, the Z, the maximized Z value, you cannot increase or decrease. No matter how many iterations you do, how many, logics you apply, you cannot make it increase or decrease because it is degenerate. It will just repeat the same answer. So now we update the Z row. This is the last step because I'm not going to update the X2 row. I will just update the Z row and, just to see the right hand side if it is improving or it is not improving. So the Z star or Z new is equal to old one minus pivot column coefficient into new pivot row. So this is the new pivot row, and the old one for Z is minus 3 by 4 0 9 by 4 0 minus 3 by 4 0 9 by 4 0, and the right hand side is 18 minus the pivot coefficient over here is minus 3 by 4. So we will put value over here, and the new pivot row is 1 0 minus 1 2 and 0. Now doing the row operation, what we get is minus 3 by 4 plus 3 by 4. It will get us to 0. 0 plus 3 by 4 into 0 is 0. 9 by 4 plus 3 by 4 into minus 1 minus 3 by 4. So 9 by 4 minus 3 by 4, it will give us 4, and 6 by 4 are 3 by 2. 0 minus 0 plus 3 by 4 into 2 is equal to 0 plus 6 by 4, 6 by 4, and 18 minus 3 by, plus 3 by 4 into 0 is equal to 18. So we will update it over here, and we get 0, 0, 3 by 2, 6 by 4, and 18. We see that the right hand side solution for the Z does not change. So this is the generate solution. You got it? Because it does not change the, the right hand side of the Z row. So this is the generate solution. So yes, so it doesn't matter if you do the 5 more iterations or 10 more iterations, the answer will remain the same. It will be 18. It will not change. It will repeat the same answer. So these kind of solutions are called the degenerate solution. And the phenomena is called the degeneracy. And this phenomena occurs when we have two things. The first one is when there is a tie between the two basic variables, and the second thing is when a basic solution, the when a basic variable in the first column have a zero solution on the right hand side. If these two phenomena occurs, then the solution is a degenerate one. It will stuck at some point, and it will not generate any new solutions to you. It will just repeat the answer. So this phenomenon is called degeneracy. I hope, you have understood both of the topics today. Yeah, this is all for the degeneration. Yes, but before sensitivity, I we have like degeneracy. We have like small topics, two or three. So if you want me to do that, I will do because it can, maybe there is a question from that. I don't know about your teacher, but uh, there are some questions on unbounded solution, infeasible solution, and degeneracy, and the special cases. Teachers usually focus on one of the special case they can bring in the exam paper. Yeah, send me your notes so that I can see like what topics, what special case